Okay, picking up with our recorded lecture, this is Chapter 2, Part 3. And what we're looking at is a motion diagram. And what you see is three distinctly different phases. Now notice that if the velocity vectors have the same length, that indicates the speed is constant. So we can see our first phase, our motion, our speed's not changing, so we have a constant speed. In our second phase, our speed's a little slower, and in our third phase, we move to a faster speed. So this becomes a lot clearer if we graph it in terms of our position versus time graph, and you can see the different slopes of our three segments. So how do we determine slope? Well, slope is the rise over run. And in this case, our rise is our delta x, and our run is our delta t. So we can take and find the slope for each of our three sections. The slope of an object's position versus time graph is simply the object's velocity at that point in the motion. Now, you can also look at the position versus time graph and come up with some other information once you have the slope. So the other information is what I just mentioned, is finding the velocity. So here, shown in a little more detail, we have our position versus time graph, and notice we're doing the slope of our first segment, our second segment, and our third segment. So you can see we have, for our first segment, a velocity of 1 meter per second. Our second is 0.33 meters per second, and in our third we have 1.7 meters per second. Now we can take that information and then graph it on a velocity versus time graph, and what you notice is straight lines in our three different segments that are horizontal. So that indicates that during those separate three sections, your velocity was constant because that line's a horizontal. It is not changing. Now I put this little table in here. It's called a tactic box, and it just gives you a little more information about what can be obtained from your position versus time graph. So first off, you determine an object's position at time t by reading the graph at that instant of time. You determine the object's velocity by finding the slope of the graph at that point. Keep in mind, the steeper the slope, the faster the speed, and you can determine the direction of motion by noting the sign of the slope. Now, when you have uniform motion or constant velocity motion, you're going to have straight lines. Okay, the top picture shows you uniform motion, and the way we know that is the displacement between your successive frames are equally spaced. So basically your dots are equally spaced. Now, if I were to take and graph this information, I'm going to get a straight line. So my object's motion is uniform if and only if the position versus time graph is a straight line, like you see in this figure. Now let's do this example where we have a position versus time graph, and you're asked what's the velocity of the object at 6 seconds. So here's our 6-second mark right here. So we're going to draw it up to intersect the line, and we're going to also draw it over. Okay, we're starting right here. So I have to find the slope. So my slope is my velocity. My velocity is delta x over delta t. So which is x2 minus x1 over t2 minus t1. So I end up at 25 meters. I started at 5 meters. My time ended up at 6 seconds, and I started at a time of 0 seconds. So I have 20 meters over 6 seconds, and I want to simplify that, and it comes out to be 3.3 meters per second. Now, if I were to look at a graph of position versus time, when I have instantaneous velocity, notice that my line is not curved. So my displacement gets greater as the car speeds up. So if I wanted to do the slope of the curve at any particular point, I'd have to draw a tangent to that curve. And then the slope of the tangent would be the instantaneous velocity at that instant. Now, our next topic is acceleration. So acceleration, or average acceleration, is the change in velocity divided by the time that it takes to make that change. So you can see here, my average acceleration is delta v over delta t. Just like we did with speed, we can talk about average acceleration, we could talk about instantaneous acceleration. And acceleration is the slope of your velocity versus time graph. Now notice the units are meters per second squared. So one way to tell if you're dealing with speed, velocity, or acceleration is look at your units, because the units for speed and the units for velocity are typically meters per second, whereas the units for acceleration are meters per second squared. Now, acceleration is a vector quantity, just like velocity was. So when acceleration is in the same direction as the velocity, the speed of the object is increasing. When acceleration and velocity point in opposite directions, the speed is slowing down. Now, one thing we don't do in physics, and that is use the word deceleration. Because in physics, acceleration includes both slowing down as well as speeding up. Now, if we go back to our motion diagram, in this case we have a Volkswagen and a Porsche, and you can see we've done a table as well as a velocity versus time graph for them. So an object that's undergoing constant acceleration is going to have a straight line velocity graph. And at any time, I can find the slope of that straight line, and that will give me my acceleration. Now, if we look at the signs of acceleration, what we see is a positive slope implies a positive acceleration. A negative slope is going to imply a negative acceleration. Your acceleration vector points in the same direction as your velocity vector for an object that's speeding up, and opposite if your object's slowing down. So if I have an object that speeds up, as it moves to the right, my velocity is positive, it will have a positive acceleration. If I have an object that speeds up as it moves to the left, it has a negative velocity and will also have a negative acceleration. This slide shows the acceleration versus time graph. And notice when the top picture is a horizontal line, that tells us that it's a constant acceleration. The bottom picture shows velocity versus time graph, also for a constant acceleration. Now, our acceleration is the change in velocity over the change in time. So notice this formula, we do have a subscript of x right by velocity, and that just tells us that it's operating in the x direction. Anytime you are dealing with motion with constant acceleration, you will use one of these three kinematic equations. You only use these kinematic equations for constant acceleration. So the first kinematic equation is used when you have it is a velocity equation for an object with constant acceleration. The second one is a position equation for an object with constant acceleration. And then the last one relates velocity and displacement for constant acceleration. These kinematic equations you want to be able to solve for every variable. The only one would be this second equation, and I would never have you solve for time unless your initial velocity is 0, because you would get a quadratic equation, and we're not going to deal with those in this class this semester. Okay, let's look at this example. So we have a Dodge Caravan that's accelerating from 0 to 60 miles in 11.3 seconds. We have a Ford Taurus that requires 8.7 seconds, and we have a Chevrolet Corvette that requires only 4.8 seconds. You're asked to think about it. Which car has the largest average acceleration? Well, it will be the Chevy Corvette has the largest acceleration because it reaches 60 miles per hour in the shortest time interval. If you look at these pictures and ask yourself which of the two correspond to the car that's accelerating, well, it definitely would be this second car, okay? Because your first car is traveling the same distance during each time interval, so it's traveling at a constant speed. The second car travels farther during each successive time interval, and therefore it's accelerating. Okay, let's look at this one. Now, in this one, you see two cars side by side as they exit a tunnel. The red car has a speed of 40 meters per second, and it's accelerating at 20 meters per second. So we have our red car speed. Our red car has a. I'll get this. So our red car has a speed of 40 meters per second, and it has an acceleration of 20 meters per second squared. Then you have your blue car has a speed of 20 meters per second and an acceleration of 40 meters per second squared. And you're asked at the instant they leave the tunnel, which car is passing the other? Well, your car with the larger instantaneous speed is going to travel farther down the road in the next smaller time interval. So the red car is passing the blue car as they exit the tunnel. The blue car is going to have the greater change in its speedometer in the next small interval of time, and it's going to eventually overtake and pass the red car. So the answer would be red car. Okay, now in this one, we're going to do a little math. So a car is traveling along a straight highway at 40 miles per hour, and it speeds up to 60 miles per hour during a time interval of 20 seconds. What's the average acceleration? So we're looking for average acceleration. We know our final velocity is 60 miles per hour. Our initial velocity is 40 miles per hour. And our time interval is 20 seconds. Now, because we have our velocity in miles per hour, we're going to want to put our time in hours. So we got to do a little conversion. So remember from chapter 1, we had, 20 seconds. We're converting to hours. So in a minute, we have 60 seconds. And in 1 hour, we have 60 minutes. So our seconds cancel, our minutes cancel, and that's going to leave us with 5.6 times 10 to the minus 3 hours. We know that average acceleration is the change in velocity over the change in time. So that's going to be VF minus V initial over delta T. So we have 60 miles per hour minus 40 miles per hour divided by 5.6 times 10 to the minus 3 hours. And that's going to give us an answer of 3571.4 miles per hour squared. Now, if we go back and want correct significant figures, we see our smallest significant digit has to be just one significant figure. So then we can make that 4 times 10 to the 3 miles per hour squared. Okay, let's try another one. So in this one, the driver of a car traveling 75 feet per second slams on the brakes. It takes the car 5.38 seconds to stop. What is the acceleration? So we make our list. We're looking for acceleration. The car, we know it has an initial and we have a final velocity. Well, initially it's traveling at 75 feet per second. When it slams on its brakes, it has no velocity because it's coming to a stop. And it does that in 5.38 seconds. So we know our acceleration is velocity final minus velocity initial over delta t. So we have 0 minus 0, let's keep our units, feet per second, minus 75 feet per second divided by 5.38 seconds. So our acceleration is negative 14 feet per second squared, which makes sense because it is coming to a stop. Okay, our next one we have automobile uniformly accelerates from rest to 15 feet per second squared for 6 seconds. What's the final velocity in feet per second? Okay, so uniformly tells us it's constant acceleration. For constant acceleration, it might say constant, it might say steady state, it might say uniformly. So that tells us we need a kinematic equation. So we can use our first kinematic equation, okay, to find that final velocity. And that first kinematic equation is Vx final equals Vx initial plus Ax delta t. So we're looking for final velocity. So Vx final, we make our list, is what we're looking for. Uniformly accelerates from rest, so we know our Vx initial is 0, and we know our acceleration is 15 feet per second squared. And again, check your units, because remember, acceleration, your time value is going to be squared, and your time is 6 seconds. So we can use the formula, our first formula for kinematic equations. So then we're going to have Vx final is Vx initial, 0, plus our acceleration is 15 feet per second squared times 6 seconds. And that's going to give us a value of Vx final will equal 90 feet per second. Okay, we'll go ahead and stop our recording for part 3.